Here's the version of this story almost everyone already knows. The sun formed, the heavy stuff stayed close, the gas and ice drifted out to the edges, and eventually you got 4 small rocky planets near the sun and 4 big gas and ice giants further out. Rock stays close. Gas goes far. Simple, tidy, done. Here's the problem with that version. It's true as far as it goes, and it doesn't come close to explaining our actual solar system. It doesn't explain why Mars is embarrassingly small for a planet in its position. It doesn't explain why the asteroid belt is split into 2 chemically distinct populations that shouldn't be sitting next to each other. And it doesn't explain the leading model for how Jupiter, the largest object in this solar system besides the Sun itself, spent part of its early life somewhere else entirely, before turning around and going back. That's not speculative fringe science. That's the mainstream, if genuinely still debated, explanation for why this solar system looks the way it does. Almost nothing out here stayed where it started. This episode is about the part of the story that usually gets skipped, and it starts with material this channel has already tracked down the origin of. The heavy stuff in that first sentence isn't generic. Every atom of it heavier than hydrogen and helium had to be forged somewhere by something first. Before anything migrated anywhere, the raw material of the solar system sorted itself, and the mechanism for that first sort has nothing to do with movement at all. It's chemistry driven entirely by heat. The solar system began as a rotating disk of gas and dust surrounding the newly forming sun, the protoplanetary disk. That disk wasn't primordial hydrogen and helium alone. It was seeded with heavier elements. The same metals. This channel already traced back to the deaths of the universe's first stars and later, colliding neutron stars. Close to the sun, temperatures were high enough that only rock and metal could condense into solid grains. Anything more volatile, like water, stayed as vapor. Further out, past a boundary called the frost line, roughly where the asteroid belt sits today, a few astronomical units from the sun, temperatures dropped low enough for water, ammonia, and methane to freeze solid. Footnote 1. I do find that the frost line conceptually is quite satisfying in a way few boundaries in nature are. It is not a wall, a membrane, or a force. It is simply the distance at which a molecule decides it would rather be ice. That single thermal boundary explains the basic split everyone already knows. Rocky planets close in, where only dense material could solidify, gas and ice giants further out, where the frost line unlocked an enormous additional reservoir of solid material, ice, for young planets to build from on top of the rock and metal available everywhere. More building material means bigger cores, means enough gravity to start pulling in the surrounding hydrogen and helium gas directly, means gas giants. Footnote 2. This part of the story really is that simple, and it's also, on its own, incomplete. The frost line explains why Jupiter and Saturn could grow large where they did. It says nothing about why Mars turned out too small, why the asteroid belt looks the way it does, or why the outer solar system is arranged the way Outer Solar System Survey found it. For those, the disk's initial chemistry isn't the whole answer. Movement is. Here's the part of the story that turns planets formed in place into something much stranger. For decades, planetary scientists had a genuine, nagging problem: Mars. In every model where planets simply accreted from local material and stayed where they formed, Mars, sitting further from the sun than Earth, in a zone that should have had more raw material available, not less, should be at least as large as Earth, probably larger. Instead, it's roughly 1/10 of Earth's mass. Something removed most of Mars's raw material before it had the chance to grow. Footnote 3. The answer proposed in 2011, and still the leading explanation today, is called the Grand Tack. Footnote 4. The model proposes that Jupiter, while the gas disk still surrounded the young sun, migrated inward, possibly as far as roughly 1.5 astronomical units from the sun, well inside where Mars orbits today. Then, once Saturn had grown large enough to be gravitationally captured into a resonant orbital relationship with Jupiter, the pair reversed course entirely and migrated back outward together, dragging much of the disk's inner material along with the tide of their passage. Footnote 5. The logic is elegant. A planet passing through a region does not need to destroy the material there. It only needs to scatter it. Mars did not lose its mass. Mars lost its neighbors. Run that scenario forward and several stubborn puzzles resolve at once. Jupiter's inward pass would have swept much of the material past roughly 1 astronomical unit out of the way, starving the region that became Mars of raw material, while leaving Earth and Venus, formed closer in, comparatively untouched. Footnote 6. The same passage would explain the asteroid belt's genuinely strange structure. It's not one uniform population, but two chemically distinct groups: drier, rockier S-type asteroids in the inner belt and darker, more carbon and ice-rich C-type asteroids in the outer belt. A split that makes little sense if the belt simply formed in place, but falls out naturally if Jupiter's passage first emptied the region and then repopulated it from two different original source zones during its return. Trip outward. Footnote 7. It's a genuinely satisfying model. It wasn't built to explain the asteroid belt, and yet it explains the asteroid belt better than any model designed specifically to do so, which is usually the sign of a good theory. Might also be wrong. Here's where this episode has to leave the tidy version behind, because the honest current state of this research is messier than most explainer content lets on. The grand tack depends on a specific mechanism: Jupiter and Saturn getting captured into a particular orbital resonance, then migrating outward together as a pair. Whether that capture actually happens depends sensitively on the physical properties of the gas disk itself, specifically its viscosity, a measure of how easily the gas resists flowing past itself. Footnote 8. Older disk models, using higher assumed viscosity values, reliably produce the outward migrating capture the grand tack requires. More recent work, using viscosity values that better match current observations of actual protoplanetary disks around other young stars, tells a different story. A 2024 analysis found that under these updated, more realistic viscosity assumptions, Jupiter and Saturn are more likely to get captured into an entirely different orbital resonance, one that does not produce the outward migration the grand tack needs. Footnote 9. The paper's own conclusion is worth stating plainly rather than softening. Based on current disk physics, it is judged to be roughly equally likely that the grand tack did not happen as that it did. That's a real, unresolved scientific disagreement, not a settled model with a footnote. And it's worth naming explicitly what that means for everything Section 2 just built. The evidence the grand tack explains, small Mars, the asteroid belt's two-population split, is real and undisputed. The mechanism proposed to explain that evidence is genuinely contested. Those are two different confidence levels, and this channel doesn't get to blur them together just because one of them makes for a cleaner story. Some researchers are now searching for grand tack-like signatures in exoplanetary systems around other stars, on the logic that if the underlying migration mechanism is a general feature of planet formation rather than something unique and fine-tuned to our own solar system, it should show up elsewhere too. Footnote 10. That search is ongoing and it hasn't delivered a clean answer yet either. So, did Jupiter actually go somewhere and come back? Probably. The evidence it left behind is hard to explain any other way. Do we know with confidence exactly how? Not yet. Whatever happened during the grand tax era, the giant planet's story wasn't finished. Hundreds of millions of years later, well after the gas disk itself had completely dissipated, the outer solar system underwent a second, separate reorganization, this one much better supported by evidence. The NICE model, first proposed in 2005, describes the giant planets starting out in a far more compact configuration than they occupy today, with Jupiter, Saturn, Uranus, and Neptune orbiting much closer together. Footnote 10. At some point, gravitational interactions with a massive surrounding disk of leftover planetesimals triggered an instability. Jupiter and Saturn crossed a specific orbital resonance, and the whole system of giant planets began migrating, with Uranus and Neptune in particular getting flung outward into far more distant, more separated orbits. This single event, or its rough equivalent, is credited with explaining a genuinely wide range of features astronomers still see today: the current, well-spaced orbits of all four giant planets, the population of Trojan asteroids sharing Jupiter's orbit, the irregular, oddly angled moons captured by the outer planets, and, this is the direct connective tissue to where this channel goes next, the structural shape of the Kuiper belt itself. Footnote 12. The outward scattering giant planets are the leading explanation for why the Kuiper belt has the layered, complicated structure it does, rather than being a simple, uniform disk. The next episode picks up exactly here, what that scattered debris actually looks like today and how much of it we're only now starting to properly count. If indeed Jupiter and Saturn spent their youth wandering the inner solar system, came home, then spent their middle age flinging Uranus and Neptune halfway across the neighborhood. At what point does a planet's orbital history stop qualifying as physics and start qualifying as a personality? Some researchers connect this event to the late heavy bombardment, a period roughly 3.8 to 3.9 billion years ago, evidenced in lunar rock samples, when the inner solar system took a disproportionate pounding from incoming debris. That specific connection remains debated among planetary scientists, in part because it requires the NICE model's instability to have been delayed by several hundred million years after the solar system's formation, which some researchers find suspiciously convenient rather than physically motivated. Footnote 13. Worth flagging honestly rather than treating it as settled. This episode isn't going to resolve a debate the field itself hasn't resolved. Put the frost line, the grand tack, and the NICE model together, and here's the actual, current best answer to a question that sounds simple and isn't. Why does the solar system look the way it does? It's not because everything formed exactly where it now sits. It's because a hot young disk sorted material chemically by distance from the sun, then at least one giant planet very likely wandered deep into the inner solar system and back out again, scattering and redistributing material as it went, and then, hundreds of millions of years later, the entire outer giant planet system rearranged itself a second time, flinging debris in every direction as it settled into the spread-out configuration we see today. Every population this channel has already spent time on traces back to some piece of this story. The asteroid belt's two species split. The Kuiper belt's layered structure, including its outer edge still not fully mapped, still possibly hiding a second belt nobody's confirmed yet. Even the sheer quantity of leftover material still scattered across the outer solar system, the exact material the Rubin Observatory is now racing to catalog for the first time, is a direct consequence of how violently this rearrangement happened. None of that leftover material formed where it currently sits. It's debris from a process that finished shuffling the deck a very long time ago, and we're only now getting a detailed enough map to see exactly where all the cards landed. There's something almost comforting in a strange way about a solar system that didn't stay put. It means the tidy diagram in the textbook, small rocky planets here, big gas giants there, everything in its assigned seat, was never really the whole truth. It was a snapshot taken long after the actual, much messier process had already finished. Jupiter moved. The asteroid belt got rearranged twice. The Kuiper belt is still 4.5 billion years later, a scattered record of exactly how much everything got shuffled. Nothing out here stayed where it started, including, eventually, us. There's still a lot of universe left to look at. Some of it, it turns out, used to be somewhere else entirely.